Hello, I'm Alexis RAYNAUD, and my research project is to create an algorithm that generates attack scenarios on cyber-physical systems. My work is supervised by Nia Nguyen, and it is part of Teoseru's thesis subject. Cyber-physical systems, or CPS, are systems that combine computational and physical components that interact with each other and the environment. They are characterized by their ability to sense and respond to their surrounding in real time. One of the key specificities of CPS is their tight coupling of physical and computational components. This allows them to perform tasks that involve both computation and physical actions, such as control and automation tasks in manufacturing, transportation, and other industries. CPS are found in a wide range of applications, including smart cities, industrial control systems, autonomous vehicles, and all the Internet of Things. So it's really easy to understand how critical an attack on a CPS can be. Moreover, engineers performing cybersecurity risk analysis are struggling because systems are getting bigger and more complex, and CPS often operate in complex and dynamic environments. It's really important to know the dynamic part, and they need to be able to adapt to changing in conditions in real time. So this required sophisticated algorithms and control systems to enable the physical and computational component to work together effectively. So cyber-physical systems are both really critical and really hard to protect. For now, most of the security analyses are made by cybersecurity engineers that rank each component of the system individually and then analyze all the components together using attack graphs or attack trees. Here we can see the first step where in a tab, cybersecurity engineers rank each component of systems. There is three scenarios. The support is a component linked with it. The impact of this type of risk, the likelihood, and then the risk level. Uh, Imagine having a thousand and thousand of rows of a tab like this for huge cyber physical systems. It's becoming really hard to understand and to understand and to analyze what's happening in it. So once cybersecurity engineers ranked all the components, they have to analyze if there is a path between all these components to lead to a critical event. So to do this, they use attack graph or attack trees. Here is an attack tree. Uh, there is a starting point, and that is a global objective on the left. Here, the goal is to manipulate traffic flow, and each branch explain a way to achieve the previous objectives. So I will not go deeper on that, but it's easy to understand that attack trees or attack graph become too complex to be analyzed by hand. Here for this example, it's quite simple, but imagine having 1,000 of attack graph, even bigger than that. For important CPS, for a human, it's hard to understand everything. Moreover, it's hard to maintain a system over time when the architecture of the system changes. In fact, this type of approach is totally disconnected from the real architecture of the system. We cannot see the architecture through this tree or through a graph. So if we underline some critical safety issue in the graph, it's hard to link it with the real components in the architecture, and changing only one component can lead to make a new attack graph that can be totally different. And due to that, it's hard to create a system that are secure by their designs. Sometimes you can significantly increase the robustness of a system by changing the arrangement between components, but the actual analyzing tools are not taking this aspect in account. So we underline that the first issue is that cyber physical systems are too complex to be analyzed or maintained over time. But another main issue is that the ways we analyze cybersecurity risks. In fact, attack graph and attack trees and all the type of cybersecurity analyzing tools are only statics one. Meanwhile, cyber physical systems are dynamic systems evolving in the real world and having many interaction over time. So here we can see a simple attack sequence or attack scenario. An attacker enter a system in the DSRC component and then go from one component to the other to attack the break control that is a critical event. And static analysis can only determine direct attack require a quite short amount of time like this, while in the real world, for example, if two validations are required to hack a wall system, an attacker can activate the first validation in the first time using a particular attack, and then later, maybe 1 month later, he can activate the second validation and access the wall system using another type of attack. And this type of process is hard to predict by looking at a static graph or analyzing tool that exists for now. So to deal with the two previous issues, keeping a real track of the architecture of the system and make the results easier to understand, and finding a way to illustrate attack scenarios dynamically. We have 4 points of interest in the literature. First, how discrete event systems formalities is used in other research. How can we rank the components of a system in terms of cybersecurity, and how can we rank a global attack path in is the path present high risk as high safety risk or not? We also have to study what can be a good case study to test our method on, and how can we implement the algorithm. So on this mind map, where each rectangle shape is an article. So let's take a look at these four parts. First, in green, there is a discrete event system formalism part. This section contains articles that concern discrete event systems. They are divided into two subsections, so that those that explain discrete event systems and or they are used or model for use cases concerning industry, because mainly discrete event systems are used in the industry. And on the left, there is an article that oriented the discrete event systems for cybersecurity's use cases. And all these three articles were written by Theo Siru, the PhD student I work with. And then on the right, in yellow, there is the ranking parts. It contains articles that describe or use a method to rank attack graphs. Those methods are interesting as they consider either each component of a system or the whole system and the overall connectivity between components. In pink, there is a case study. So in order to test our work on a real cyber physical system, we had to find an interesting case study. So we found the Evita project. It's a really good case as it's it is really well documented, and many systems and vulnerabilities are described. Moreover, this project has already been used by Theo Seru in these articles. And the last part in blue on the left is the implementation part. So as our work is to implement an algorithm using a discrete event system, we found articles giving a framework to do so. And in addition, we think that it can be interesting to use optimization techniques as explained on the by the two articles at the bottom. So our positioning for our work is to use a model-based approach to keep global architecture of the system. We also will use the discrete system event formalism, and we'll also create attack scenarios using object-oriented event graph. So the last 2 points will help us to create dynamic attack scenarios. And for the ranking method, we will use two ranking methods to rank each component of cyber physical system separately, and one to rank the overall connectivity of the components in the systems. And finally, we'll try our algorithm on the Evita project. As we use the discrete system event formalism for our study, it's important to define it. Before starting, it's also important to note that the articles written by Theo Seru in 2021 were fundamental for us, and it depicts the formalism of discrete event systems used for modeling CPS. His works aims to study cyber attacks effects on and impacts on the safety of the systems. So the discrete event systems, also called DES, is a mathematical framework used to model and analyze a system that operates in a discrete time step and involve the occurrence of discrete events. In the discrete event system formalism, a system is represented by a set of states, a set of events, and a set of transitions between states that are triggered by the occurrence of events. The behavior of the system is defined by a set of rules that specify all the system transitions from one state to another in response to the occurrence of events. For our case, each action an attacker can do to access a particular device is an event, and each action of the system can do to protect itself it's also an event. The discrete event system formalism is used in a variety of fields, but for our case, as far as we know, as far as our knowledge, it's one of the first time, maybe the first time that discrete event system formalism will be used for cybersecurity and risk analysis. One of the main advantages of the discrete event system formalism is that it allows us to analyze and predict the behavior of a system using mathematical tools and techniques such as graph theory, automata theory, and probability theory that can lead to represent, for example, self-reconfiguration of the system during an attack. The representation of an attack became dynamic, and this can be used to drastically reduce the number of results by automatically eliminating not critical scenarios, as our goal is to detect and generate attack scenarios. So for the ranking part, we'll use one main ranking method, This article, Cyber Physical Component Ranking for Risk Sensitivity Analysis Using Between Centrality, presented by Amarashi Umunakwe in 2020. It explains ranking method for each component of cyber physical system. This study presents many tools to evaluate components such as the cyber physical betweenness centrality. It's an index, also called the CPBC index. This index aims to rank the cyber physical system components in order of importance. This index uses scores computed based on the common vulnerability scoring system. The use of this index seems to be a good method to appreciate the criticality and reachability of each component in CPS. And with the discrete event system formalism, we keep a track of the architecture of the system. Having a rank for each component can help to create a global rank for an attack path exploiting different components. Moreover, to rank the overall connectivity of the system, we will use the PageRank algorithm. That is basically the algorithm that rank all the pages on the internet. So it's a pretty effective algorithm to understand the connectivity of a graph. So talking about graph, the graph we will use is the object-oriented event graph. In fact, in order to create a dynamical detection of attack scenarios with the discrete event formalism, we found this article, object-oriented event graph modeling formalism to simulate manufacturing system in the industry Cat 4.0 era, written by Lorenzo Tiassi in 2020. It presents a new type of graph. We call it object-oriented event graphs, also called OOEG. This type of formalism is suitable to represent discrete event simulation models. In this paper, it provides a complete description of a discrete event system and explain how OOEG are a good type of graph to represent discrete event systems. Bonus for this work is that it explains how the object-oriented approach allows linking states variable to objects, making the model more understandable. So we use the methodology given in this article to build our own object-oriented event graph. This article gave us a good tool to fully represent discrete event system without any information loss. Moreover, it provides an understandable graphs that stick to the real system architecture, so it's way more understandable for engineers, and it's one of our goals to present clear results. So this is why we use object-oriented event graph. Finally, we used an automotive case study of the Evita project to challenge our model. From 2008 to 2011, members of this project have worked on a unified approach to security and safety risk analysis for automotive onboard networks. In addition, they have developed a relevant use case and several security threat scenarios which are available online. Therefore, we view this project as an opportunity to use a case study widely accessible and to challenge our model, even if it's not up to date. It's still good to use. So to conclude, after all, find the possible title for our work is a dynamic attack scenario generation algorithm based on discrete event system formalism. as we want to generate attack scenarios in a dynamical ways, and everything is based on the descriptive and the formal needs. After all, thank you for your attention. I hope you understood everything. If you have some questions, do not hesitate to reach me with this email address. I'll say you goodbye. Have a nice day.